Okay, thank you very much for invitation. So today I'll talk about kind of deep reinforcement learning stuff for robotics applications. So quickly, kind of overview the reinforcement learning. It's basically about it's a very general framework for problem solving, and it's basically about the agent interacting with the system. So the agent at some state takes some action, the state changes according to some dynamics, and then you also kind of receive the reward. And the goal of reinforcement learning is to find optimal policy that maximizes the cumulative future return you get. And naturally has many kind of potential applications that can be framed as a reinforcement learning problem. So before I start, I want to kind of start with quotes. So when on the time I was back undergrad in Toronto. So there was time I started going machine learning, but it's really kind of saying something that once the kind of scalable machine learning algorithm, be it kind of human engineered solutions, basically there's no looking back from that. Because once you just scale you just collect more data, you increase the compute, and you keep improving, and human cannot catch up. So what's really kind of tipping points for machine learning takeover at different applications? So on this graph, one axis, I show the available data. The other axis, I will compute, no bias or some stuff. And say this area, pretty much kind of area, I think probably a lot of people agree that basically machine learning has taken over the traditional systems. Computer vision, speech recognition, especially. And in natural language processing and, say, reinforcement learning simulation domains, it's kind of getting there. It's kind of a bit more challenging because, say, for NLP, the format of data is quite different. And in reinforcement learning, sometimes the problem is kind of much harder. But there's not much to worry about those because as the completion increases, eventually this will be. The problem is really kind of with the real world applications where the completion can increase. The question is, what kind of stuff can you do? The point where the machine learning actually makes. So I'll kind of quick over kind of three branches of reinforcement learning. Kind of one way to classify it. I'll classify based on those three categories. So the first category is kind of model-based reinforcement learning, where you, based on samples you have, you try to estimate the dynamics model, the action, how it's conducted. And basically, once you have the model, you can just plan, you can do optimization. Second one is off-policy arrow. And one of the most famous algorithms is the Q-learning algorithm. It's basically looking at all the experience you collected so far. And it's kind of doing some kind of approximate dynamic programming to see what kind of, in this case, what action would have led to kind of better outcome, and then try to estimate of that action and kind of greedy improve the policy using this kind of reflection style at high level. And then on policy method, it's kind of one of the simplest. You just differentiate the original reinforcement objective, the parameters, and it's pretty much corresponds to trial and error. You just roll out your current policy you have, and just reinforce whatever that worked better than the other. Each of those methods kind of has different limitations. The first one is limited by the model, especially for dynamics that involves a lot of, say, contacts. The model is known to be like, it's just discontinuous, so model-based planning pretty much fail a lot. And then off-policy learning is kind of limited by kind of how good your value estimate is. And that kind of depends on how much sample you have and if you're using like complicated Q function or not. And I'll describe them more later. And the last approach, the on-policy stuff, is kind of limited, fundamentally limited by the variance. It's optimizing the original reinforcement objective you care about, but the gradient estimate you get out has pretty variance, I will show later. So this kind of show those kind of three approaches in the graph. So on one axis, you have kind of data intensity, how much data it takes to solve the task. The other axis is more kind of how hard a task those algorithms can solve. So model-based is sample efficient, but there's kind of limit to how hard a task can solve. Off-policy is a bit better. It can solve kind of harder tasks, but it usually takes much more data to solve it. And naive kind of on-policy stuff takes even more data, but because of some property I'll describe later, it can solve harder tasks. So eventually the goal is we want to really bring those kind of stuff to the region on the kind of top left, where you want to become data efficient.
It's a tricky problem, but that's pretty much the goal. And my research so far in reinforcement learning has been kind of focused around this area. So try to bridge between model-based and then set up policy model 3, or like bridge between off policy and on policy, and try to basically reach that. And
I'll talk about these two.
So
one is basically kind of looking at currently kind of model-free methods
and see if those
actually solve some
of your reward problem in the world.
and then we actually scale it. Second one, the Q problem is talking about can we kind of drive some kind of algorithm, the good part of the off-policy and on-policy algorithm. So
this is just
running standard Q running.
this is Q function. This functional task, which is kind of grab the state and move to some targets. And
it can solve tasks that the model base cannot solve because this has a lot of contact dynamics. It's pretty hard. There's some problem. It takes like 1,000 trials, so you can kind of see it's reasonable, but ideally you want to do it with less. And it's kind of sensitive to hyperparameter because using a neural network to kind of policy or the Q function. And so I'll talk about how can we kind of improve in those aspects: efficiency, scalability, and then stability. So for the scalability, the most naive thing you can do, or the kind of say the almost Google way of doing thing, is just use more robots. So you have a lot of robots collecting the data in parallel. Then you can just increase the rate at which data comes. And that's why I show in this paper that you just use multiple robots, collect the data, and you can basically train to open the door in like 2.5 hours. So just robots exploring at 20 minutes, and after 2.5 hours,
it's like exploring the way that open the door quite often, and this is kind of final policy data.
and
This is kind of training
without any demonstration.
generic policy, quantitative engineering, and compare using one versus two robots, using significant improvement, using robots. And the policy is also kind of robust. You reach some level of service, so it's kind of you actually know it's got to and then push it off. And basically information also comes from the policy, and can learn how those kind of tasks better than some of those technical.
I really like comparison on K-scale. Is kind of what we're showing. So with two robots, 2.5 hours, we can teach you open the door. Imagine what we can teach if you have 100 robots or 1,000 robots.
What kind of
reward function? Yes. So it basically knows the states of the robots or the joint angles, and then it knows kind of how much door is opened, and the door is kind of fixed, so we can just kind of try it, and you don't really know the position of the door. For multiple position door, we try in a simulation, and then you just put it, and you can learn it. And reward is just how far the hand is close to the door, and then how much door is open. Okay, so now that's kind of off-course reinforcement learning. But something I want to go to is basically kind of how can we do something better than this? So this kind of tries to summarize the kind of off-policy and then some of the on-policy methods. So on the left you have off-policy, and it's an actor-critic algorithm. It's very simple. You basically learn the Q function that
corresponds to the value of the policy. The Q function is this data action to
policy. What's the cumulative return you get in the future? It's kind of summarizing
policy. You basically learn the Q function using the policy and then also the policy
this one has kind of low variance gradient.
It's not efficient because you use old experience. It's relatively efficient.
Old experience you collected. But your bias is kind of bias gradient because often
the Q function is incorrect. And it's less stable because on the right you have this kind of policy naive metabolism. You basically differentiate and then you get this kind of store function gradient. So that's you have this example.
So this is unbiased gradient of the
and you have to design that it should be stable. But then the gradient has really high variance.
So what it means that each time you update the
policy, you take many samples, many trajectories, and then you can average the gradient and gradient estimates. and then only then you can make a stable. So it's very sample intensive.
It's also bad because after you make one update, you cannot
release the experience. They run.
All the experience you used to update the phone from the So basically one by efficiency, the other product.
They have some levels of actual goals. And this one is so what it does is basically
derive from control variance. That is where you just subtract the kind of critic estimates of the advantage function, and you can add back the correction term as you do. And depending on kind of the parametric form of the critic that you're learning off policy, you can basically derive the gradient through the
correction term.
What it does is basically the second
term will pretty much be like the gradient, so you have
low variance. And the first term will be kind of residual, the correction such that remains unbiased. But it can be from the second term. And then the nice thing is critic.
And you learn off policy, because in all experience of correcting. And in some conditions, it can sound efficient and stable. And it's quite simple, so you can just kind of plug this into any of the whatever policy grading value. And one negative is it requires significantly kind of more compute than the policy model, because you fit into this critic at the same time that you can run the policy.
But in practice, it's not a problem because in practice, you
bottlenecked by the rate at which you collect the data. So you can actually afford to quite a few complications which data factors. That is not a big problem.
And another problem is, of course,
the natural question is when does it settle? So the problem is when we use the variance, when does it mean that it's not biased? So we just think about the variance. And basically some derive from control variance, so you want to estimate some expectations, say the bar, and some estimated attribute. And let's say for G that you can subtract and add, assuming you can get the G and the expectations. Then the variance is basically how uniform and conditionally, and variance is basically variance of estimations. And we have
kind of similar tricks
in control variance and derive adaptive problem. So here we kind of implement this with an additional variable that controls the strength of the control variance, which states the serum remains unbiased. And then you can just think about the optimal A pattern. It's guaranteed to basically reduce the variance of A hat minus A bar. And if
that's pretty much the expression.
There's 1 minus the correlation between A hat and A bar. So if
they are in any way correlated,
positive or negative, we can compute this on eta, but its variance is guaranteed.
Well, it's a difference. The difference is not the variance we care because we additionally have this kind of score. But to make kind of some of the to derive complex algorithm, it's and even with that, it's pretty hard to estimate this kind of
exactly. So let's take a look at simple practical thing, which is you just check the sign of this. And you only do it when they kind of agree with sign, and if they disagree, then the perfect is bad, so you want to use the greatest rules. The results I've shown, I just will do so this is kind of comparing the Q
plus the RPOG,
which is the start, so we are policy method against the RPOG alone, and then the DPG, which is state we are of policy method for against control.
So this is the example built on Cheetah.
And it's basically
the red curve is the Q-prop.
So the Q-prop is significant on sample pressure, so then the blue curve is the RPO policy. And
but in this thing, the theory of policy method, like DDP, sometimes do much better than any of the on-policy stuff, for some reason. As it gets harder, this kind of flips a bit. So playing this is humanoid, is significantly harder. And then in here, the thing is the DDPG basically suffers, basically doesn't learn. It just plateaus at like 500. While the TRPO and the QPRO basically continuously kind of learn. But on this domain, basically Q learn significantly kind of more sample efficiently.
So
it's more stable than TRPO-GAE, more sample efficient than TRPO-GAE,
more stable than GAE, and it requires
also, for example, for humanoids, for TRPO to work, for each update you have to use 25 episodes. So you kind of make this kind of like a
But for the few problem, we're actually just do it with just 5 episodes per upload. So this is kind of nice and concrete about it. So yeah. And we tested on other benchmarks in this open engine, and then it was kind of hold across. So
I'll kind of summarize. So it's kind of interesting that deep reinforcement or approach to robotics is actually kind of surprising, kind of close to practical. A lot of manipulation tasks, we found that just off-C learning algorithm is actually kind of stable enough to learn a lot of stuff in the very reasonable kind of sample complexity. So we just have some off-policy lesser than multiple robots and probably can solve a lot of tasks. For locomotion tasks, kind of a bit harder, then you probably need more and maybe some improvements on QProp or those kind of algorithms that combine their own policy of policy.
Or those with a model-based
directions to move. Definitely, this is not.
So definitely much. And then the same thing is we cannot.
It's pretty hard to just be like there's no limit how much sample efficiency can be. The thing is, and probably one of the important things is we kind of think about this kind of role simulation, trying things with robotics.
Yes.
A lot of roboticists basically they don't believe anything about simulation. They want to transfer the controller, say, from simulation to real, and then controller depends a lot on dynamics, and basically will fail for sure. But something that would be good is that the learning algorithm that could work in simulation, say with reasonable sample efficiency, has much better chance of transferring to real world. So when we were trying the door opening task, we tried a lot of simulation. We saw the sample efficiency, kind of how stable it is, and then we just tried on real, and then and it worked. So even trying things a lot will give a lot of confidence. And what kind of caused a lot of kind of speed up in machine or like deep learning, machine learning is really kind of how you can iterate, and simulation can provide the environment you can iterate, and probably it's a place you can experience kind of much harder task. There are new algorithms because as you try harder tasks, you really kind of encounter much newer challenges that you don't if you stick with simpler ones, and hopefully that can accelerate. And hopefully the three communities can come together and try to make more progress. That's a tricky thing. So this some of the work I described here is collaboration with a bunch of amazing people. I'd like to thank them, and then thank you very much for inviting me to give a talk. Open for some questions.
What is the difference between deep unsupervised learning